Hello, hello.
Yes, sir. Good evening.
Okay, good evening. So today we will start the second session of our uh, course, quantum mechanics and molecular spectroscopy. So first day we have discussed about uh, assignment zero, that is uh, about the basics of quantum mechanics. So today we will start quickly recap uh, the first uh, uh, first week lectures. So, ha- have you gone through the lectures of quantum mechanics and molecular spectroscopy?
Yes, sir. Yes.
Okay. Then before to the assignment one, we will just quickly recap the whatever the classes we take this in last lecture. So okay. So if we remember correctly, so one minute. So so first in lecture one, we, we derived from classical wave equation to Schrodinger picture. So in classical wave equation, the wave function is dependent on space and time. So a wave function which depend on space and time, it it will follow this equation where
Excuse me, sir. Your
yes,
screen sharing is not happening.
screen sharing is not able. Sorry.
Okay, sir.
Okay. What? Sorry. Okay. I think now is it visible? Hello. Can you see the screen? Hello. Is it visible? Hello.
Yes, sir. Yes. It is
Okay.
coming. Now it
Okay.
is coming.
Okay. Okay. Let's see.
Yes, sir.
So, so where C is your okay. This where C is your speed. Okay. Of the particle, light, whatever wave function is there, the speed. So this is the position dependency. This is the time depend. The time dependency is position dependency. So if you look at this kind of equation, we can quickly know the solution should be like this. Where this thing alpha is written as 2 pi x by lambda into t. So this is called as phase factor. Now two different equation we want to impose here. One is Planck Einstein equation. It says E is equal to h nu. So nu can be written as E by h nu. Sorry, h. Another is Broglie wave equation. It says lambda is equal to h by p. So using these two, we can replace the phase factor. So we replace lambda with h by p. So we'll get x dot px by h. On another side, e dot p by h. Okay. So px is the momentum along x-axis. Okay. So now, if we incorporate this thing, so d dt of comma t, then okay, then I into d alpha by dt, then what we will get? E by t by h, and we will left with k I alpha. So this equation will be E I h. There should be one term. Okay, we can write it like this: h dot px e dot t by h cut, where h cut is h by 2 pi. Okay. So this is h psi x comma t. On the other hand, if we take its space derivative, then similarly we will get so both of the case we found we are, if we take a derivative with respect to time or with respect to space for psi xt function, we reproduce the psi xt with some constant. In time case, we are getting like this I e by h cut. In space case, we are getting I px comma h bar. So these kind of equations functions are known as eigenfunctions. Where and these are the eigenvalues. Okay. So now, therefore, if we look right right like this, next page, then we will get I e by h cut I e by h cut psi x comma t. So I take this thing, then just move it here. D psi xt by dt will be your e of psi xt. Okay, another way, dxt by dx will be your ipx. So from here, actually, this is the expression of momentum operator. In classically, what momentum means in classical picture, E is equal to momentum is equal to mass into velocity. Velocity is nothing but time derivative of the position. Okay, but now in
So,
hello, hello,
yes. So your only voice is coming, but the screen is remaining black.
screen is remaining black.
Are there any problem at your end?
1 minute, 1 minute. Let me move it and share it. Can you see this red line on the screen? Hello. Now
Yes,
it is.
yes, sir. Now it is coming.
Now it's visible, no?
This may be my network is not stable enough,
Okay.
so it is getting.
Okay. Okay. So, uh, okay, you can see that in classical picture, the momentum is a time derivative, but in quantumically, it goes to the time from time derivative to position derivative, phase derivative. Okay, this is actually known as momentum operator. With this, actually, we are now ready to answer our first question of your assignment 1. The question is the correct statement in the following is or are. 1. The time dependent Schrodinger equation is a total energy eigenvalue equation. Then IH cos dy dx psi x comma t.
So in question paper it is time independent.
What? Hello?
Number one is time independent
It's sign.
instead
Sorry,
of
sorry.
dependent.
Yes, sign independent.
The time independence should
Yeah,
inherit.
yeah, yeah. Where E is energy of state psi x comma t. Dot IH dot d by dt. Hmm, hmm. Okay, so these are the options. So which one will be correct? So before uh, choosing anyone, we can, if we look at the previous slides, we can just tell that this is a wrong one because this should be px. So this is not a correct option. This is incorrect. Similarly, px, this is also incorrect because if we take the time derivative, we will get the energy, not momentum. So this is also incorrect. Now, for a given eigenvalue equation, c square is a c square size side. Then what will be the eigenvalue? So if you take psi and c is a operator, then c psi, okay, then this is will be the a will be the eigenvalue. Next, if we take c square psi, that means c of c psi, then we can say that this is will be a psi. Now a is a constant, a is c psi, and c of psi will produce a of a psi, that is a square psi. Now this is in question, it is written as psi into 1. So a square is equal to 1, then eigenvalue should be plus or minus. So fourth option is also correct. So this is the correct answer. And now look at the first one, the time independent Schrodinger equation. So we know the time independent Schrodinger equation, that is E plus V. Okay. So this total. This is total energy equation, and you know H psi is equal to E psi. So this is also a correct option. So this is the answer of your first question. Now with this, next let's look at the second part of the question. Question number 2. I hope my slides are visible. Okay, let's get back to the question number 2. Statements. So options are the time dependent equation I h cut d by dt x comma t h h t b for a quantum state the time dependency is governed by the total energy operator of the state. Next, C is kinetic energy operator depends on the position as well as time. Third, potential energy, shear energy operator can never be independent of time. Okay. So we have to find the correct statement. So the first one is, we know, we derived some sometime before. The first one is correct one. Second one is For a quantum state psi x comma t, the time dependence is governed by total energy operator of the state. Yes, because this is not is like now kinetic energy operator is depend on position as well as time. So this is something which is not correct. Now how it's not correct, that okay. So kinetic energy operator depends on the position as well as time. So this is incorrect and we incorrect. Now if we look at the expression of momentum operator is I h cut d of I h cut d of dx. Now if we look at classically, P is equal to mv, where T kinetic energy is half mv square. So if I take it P by 2m mv whole square, so it will be P by 2m p square by 2. So now if we want to take p square, then we have to consider is p dot x into p dot x. So I h cut d by dx of I h cut d of dx, then it will be plus I square h cut square d2x dx2. So this will be h cut square d2x dx2. Then kinetic energy operator should be h cut square by 2m d2x dx2. So kinetic energy operator is independent of time. Okay, so this option is incorrect. Now potential energy operator can never be independent of time. Now if we the perspective of this course is uh, how a molecule excites. So if the molecule is excite, it is a time dependent phenomena. So as we look at this equation, that if we consider Hamiltonian is a sum over P and V. P is kinetic energy, V is potential energy. Then where the time dependent part will come? That will only come on the uh, in some form of potential energy. So this the potential energy will be time dependent, not independent. So in some cases, however in however in the first module you said for a stationary state, we take that approximation Vx is equal to Vx comma t is equal to Vx, but this is not true for all phenomena. So we have to take that potential energy operator can be independent on time. Okay, so this is also incorrect. So these two are the correct answer. Now moving to the third one. The, Okay. So first question is that Hamiltonian can be written as h v x t plus h square by 2m. So we know h is a Hamiltonian is sum of t plus v. Okay. So T is kinetic energy. This is P, potential energy. So this is I have shown you, and potential energy is a function of x and t. Okay. So first option is incorrect. Now for a harmonic oscillator. So for harmonic oscillator, so if you think a spring like this and just tie it on a box, if you apply the force, uh, well, this is a for a mass, then the restoring force will be k into x. So k is the difference between distance covered and distance equilibrium distance. Okay. Now potential is, see, this is a expression of force with respect to potential. So potential can be written as, in harmonic oscillator, this can be written as x. So v should be half of k x square, where k is known as force constant. So as we know, T plus V is Hamiltonian, then kinetic energy is all will be h cut 2 by 2m d2x by dx2. Now this term will come half of k x square. Now see that the second option is correct. Now what do you mean by free particle? So free particle means the particle when if you look at a particle in a box or particle in a 2D box, we just say that free particle in a 2D box, free particle in a 1D box. That means in that area the particle doesn't feel any potential on it. So this for a this question where is written for a free particle h is equal to vx minus h cut by 2m by d2x by dx2, where vx not equal to 0, that makes this the option incorrect. So for a free particle, vx must be 0 for free particle. Now you can see it here, Hamiltonian is a sum of t and v. So it cannot be the difference between two. So that is also incorrect. So one option is correct, that is for a harmonic expression of Hamiltonian for a harmonic oscillator. Okay. So now where the questions come of harmonic oscillator. So next question is on something. One particle in a box. So Question 4 is, oh, now let's start from the bottom of the questions. Okay. So, what is the expectation value for a wave function psi option of sorry, for a operator A is given as psi m a psi l. So, expectation of any operator, suppose psi I, sorry, for any operator A is nothing but psi I A or psi I. So in Brian K notation you can write like this. So expectation should be for a same state. So this option is incorrect. The correct one should be psi m a psi m or psi n a psi n. Now overlap integral, this is correct. Now action integral will, this is action integral is represented psi n a psi n. So this is a expectation value. This is not an action integral. So this is also incorrect option. Now something comes in our picture, that is overlap integral between state 1 and state 2 for a particle in a 1D box system is 0. So for that we need to know the expression of a wave function in particle in a 1D box problem. So for that we have to consider this system. So if we look at the particle in 1D box problem, so this this is a to infinite wall. Okay, gap between these two wall is L. Now in between this wall the potential is 0. Out of this wall this potential is infinity. Okay, so now the particle inside the box is a free particle. So the Hamiltonian, which is denoted as T plus V, will depend on only T, because V is 0 within the box. Okay. So now if we say H psi is equal to E psi, then it will be written as H squared by 2m del 2 del x2 of psi as it a time independent Schrodinger equation if psi is a function of x. Now with this thing should be solved using second order differential equation, which will give you with some boundary condition some sin n x pi x into l, sorry, with some constant. But this is not science. The thing is that in quantum mechanics, if you get a wave function, if and if the wave function to be valid, it should be normalized within the limit. Okay, so normalization is needed. So within 0 to L, we have to normalize it. So this C is a normalization constant. So we need to derive what is the expression of C first. Then we will do the, we will jump on our question. What is the overlap between the psi 1 and psi 2? Now if we put the value of C sine n pi x L into C sine n pi x by L. So C square if you take 2 out, So this term will be eventually 0. So for all value of n. So this is a normalization constant. The expression of psi in a particle in a box problem is for a n quantum number 2 n over 2 by n n by x by l. Okay? And corresponding energy will be n square a square 8 ml square. Now n should be start from 1 to infinity. Okay? Now if I look at the, now we have to look at what will be the overlap. Now if we draw psi 1 and psi 2, the wave functions looks like this, and psi 2 will be okay. So uh, this image should be more correct. This is distance is L, so this is a node over here. Now if you look the overlap integral, which can be written as 2 overlap integral between 2 and 1. So if you superimpose psi 1 with psi 2, then the need wave function will be 0, will be vanished. So overlap integral between uh, between state 1 and 2, a particle in a box problem will be 0. Okay, so the option this is also correct. Now you can do it in different way also. So how you can solve it is something like this: is 2 1 psi 2 psi 1. Now put over 2 n sine 2 pi x into n into root over 2 by n sine pi x to dx. So 2 by n sine 2 pi x n sine pi x into n. 1 by n. So we can rewrite it as cos function cos a minus, this is a and b, this is a minus b. So minus cos is a plus b. Now, if you take an integral, it will give you sine function. Hmm. So this term will be 0 for all n. Okay, so it can be derived as using the simple integration. Okay, so this is also another approach to answer this question. Okay, then question number 5. Now we have to hurry up, otherwise it will not be finished within time.
Sir, what will be the availability between state 1 and 3? Suppose.
Yes, yes, yes.
What will be the availability in 1D box um, between states 1 and 3? Suppose.
State 1 and 3.
I think
Just
it will be non-zero.
it should be non-zero, but there is a value. Just check it using this equation, because 3 will be like this.
That means alternate levels have non-zero availability.
Yes. 1 and 2 has
Okay.
0 overlap. Just check it with psi 3 and psi 1 with this uh, uh, whatever the, you can look at this uh, profile also. Otherwise, you can do this simple approach of integration. Okay.
Okay.
That's why it's sometimes it's difficult to visualize with the equation, with the picture. So it is better to do some simple mathematical calculation and get the answer.
Okay, sir.
Hmm. For a free particle state, the the quantities that show time dependence among the following are Lx, B, Lx square, C, L square, P, X. Now, there is a hint. Now, so for a for a particle, sorry, for a operator to show time dependency, so this equation must be satisfied. And if this commutation property, sorry, gone zero, then their their time dependency will not be observed. So suppose you want to excite a molecule as a perspective of your of the course. So for exciting a molecule, we shall provide some energy in terms which will be act as a some perturbation of the system. Okay, now the perturbative part should be should not commute. If it commute with the Hamiltonian, then this this value will be goes to zero, and then there should not be any excitation in the molecule. So for a state to show time dependency, this value should not be zero. Okay, so now, so we have to find out what will be the value of this all, whether these are zero or not. So these things I have done in the last week. Okay, so here we see the first one will be zero. Okay, but other three will not show zero, will not commute, or the value of the commutator will be non-zero. Okay, so these details are there in any books, or you can see my previous session also. So the x component of angular momentum commutes with Hamilton, but their squadratic term is not commute with the Hamiltonian, as well as the space part is also not commute with the Hamiltonian operator. So if if these three things will show time dependence. Okay, so the correct option are these three. So for if this type of question is on, we have to look at the what will be the commutation. Is there any commutation property or no? Okay. Now the correct statement No, these are the option, and question is a correct statement about Hermitian operator. So if two Hermitian operators commute, then they cannot possess any common set of eigenfunction. So if two commute and A and B both are eigenfunction, Hermitian operator, then they can possess a common set of eigenfunction. This is a rule, and it it can be shown in various aspects in the uh, this course also. Okay, in quantum mechanics also. Now, all the eigenvalues of the Hermitian operator. Sorry, this is the incorrect option. All the eigenvalue of Hermitian operator must be real number. Okay, so take the example of Hamiltonian operator, which is a Hermitian. This what it gives? It gives energy. So energy can be measured. So it's a real number. So this option is correct. Now, the relationship F A G. Okay, so we can write it psi F A psi G. If you look at the lecture, you can see that it can be written as G, which is in terms in course you can written as a psi G star A psi F. So this is, if this thing is satisfied, then we can tell that F and G are eigenfunction. This is only satisfied when F and G are eigenfunction of Hermitian operator A. Now, the quantities F, A, and G and H G are real are numbers. Okay. See, uh, if this thing is a overlap integral kind of thing, it can be zero, it cannot be zero, depending on the criteria. And similarly, this thing also, it can be zero, cannot be zero. But the thing is that the results are numbers. So this option is also correct. Moving to question number 7. For an after two-level system, a state of the system is given. for a unperturbed Hamiltonian now this question is talking about some two level system, the building block of a time dependent perturbation theory. The energy of this state is E1 and this state is E2. Okay, the Hamilton wave function is a superposition of a two states A psi 1 E1 E by H cut plus A2 psi 2 to H cut. Okay. Now, without any perturbation, things that if your perturbation is light, then the light is extinguished, no light is there, so no, there is no perturbation. Then your Hamiltonian is can be written as H0. Now H0 psi 1 will result E1 psi 1 and H0 of psi 2 is E2 psi. So in unperturbed condition, the first answer and the first option is correct. Now, now if this nature of psi 1 and psi 2 are orthonormal, but this orthonormality is doesn't depend on the H0. So orthonormality means if we take psi 1, we will get a value of 1. But if take a overlap between psi 2 and psi 1, it will go to 0. So this property is known as orthonormal property. So this thing is doesn't depend on your Hamiltonian. So this is incorrect. Now the simple thing, a A1 square is the probability of the measurement, probability that measured the energy which yield to E1. It can be it can be tell with this by seeing this question also. This is also correct. Now, if psi t is normalized, then A1 square plus A2 square is 1. Let's see. It will hold or not. Psi 1, psi 1 is known as or is normalized. Hmm. So, if you normalize, then if we take integration over a space, that should be normalized. Okay, so the yield value of 0. Now, let's take A1 psi 1 and it's so in integration form, so we have to take its conjugate. Then we multiply this with this. Now we multiply this one with this. Now this with this. Now this, so this is fourth term, this is third term, and this is third term, this is second term, and this is first term. Now, yeah, the thing is that we know there is some condition, orthogonal condition where psi to psi or psi psi 2, which can be written as is 1. This is and psi 2 or psi 2 psi 1 is 0. Orthogonal, this is orthogonal property. And as a whole, it can be written as orthonormal. So, if you look at this function will survive. This psi 2 star and psi 1 is there, it will go to 0. Similarly, this term also goes 0. And now, this term is also surviving. So, it should be two term, now this thing will be 1. So what will be the left? A1 star square plus, sorry, A1 square, and from here it will be A2 square, and this written is 1. So the answer is correct. So if psi t is a superposition of two states 1 and 2, then and psi t is normalized, then the summation of their probability of two states 1 and 2 will lead you 1. Okay? So in question 7, if for two level of system, so a two level of system, then 1 and 2. So 1 is, so 1 and 2 are basis, then superposition of the state is written as E1 into 1 E2 into 2. So these two, for a time purpose, time, this is a function of time. So the question, this is this, in that question, this A1 and A2 whatever is written, they are all function of time. So this option is correct. As this option is correct, this option is wrong. Now what it says, psi1 ht psi1 is non-equal to 0. Now if you think in particle in state A is given some perturbation in such a manner that the molecule is still be at state 1, then you cannot distinguish the particle whether its energy is affected by the Hamiltonian or not. So in this case, this term psi 1 ht psi 1 must be 0. So this equation is also incorrect. Now if ht is Hermitian, and you know ht is Hermitian, and uh, then it it follows, because we show that the criteria of Hermitianity, okay, for a operator to be a Hermitian. Now the last two, particle with length of with vector k 2 by lambda is. Now, as I mentioned in the first question, the particle in a box, momentum of a particle can be written as So this equation is known as de Broglie equation. Now here in this equation we have to incorporate this term 2 pi by lambda, where k is wave vector or length of a wave vector. So lambda is 2 pi by 2. Now if we substitute this value in the, if it is equation number 1, okay, so if we substitute equating the value of lambda in equation 2 in equation 1, then q by k is equal to h by t. So P is equal to h into k by 2 pi. So we know h card is equal to h by 2 pi. So we can write the P is h card to k. So this is the calculation. So this is the calculation. Now the last question of this session. The x component of angular momentum px is given by operator and the commutator the this is the hint, and the options are heat function, psi, will not be simultaneous eigenfunction of x and px. Precise Now the question what they say, the px, they have given the px value and they given the commutator between x and px. Now you can see that px and x doesn't commute. This value is not 0. Then you, it can be said that you can precisely measure x and px for a state function psi. So the second option uh, is incorrect, as this value is not equal to 0. So for a commutator, if if a and b commute, then a and b can be assigned precisely. Same rule of commutation. Okay, I have discussed it in uh, last tutorial session. So as you see, this value is IH card, which is not equal to 0. Then you cannot measure x and px simultaneously. So this is an incorrect option. Now easily you can tell that a dot b should not be 0. So this option is also incorrect. Now if you put this value IH card, so if there is no negative term, then we can remove the modulus. So this value will be, this is correct option. Now state function psi cannot be simultaneously eigenfunction of x and px. So I have said that if these two operators commute with each other, they simul uh, can have common set of eigenfunctions. As x and px are not or non-commuting, they cannot have same set of common functions. So state function psi cannot be a simultaneous function of x and px, which is a correct option. Okay, so our question number 2, question number 10, a and d are the correct options. So with this, our first or second tutorial is assignment of the week 1 is done. So if you have any questions, so you can ask, and later we can, if I think I have some time to discuss about uh, module of the lecture of second week, and we will go perform the week 2 assignment in next week. Okay, so now if there is any confusion and any question, please ask. Uh, we have some time to discuss now. Otherwise, I will quickly go do some uh, demonstration, or some homework is given in your course. Now, if you look at the like week 2 lecture, it actually shows about how the how the probability of a wave function is changes with excitation. For it, start with a simple two level of system where superposition of two state is written as a1 1 e I e1 h cut plus a2 t 1.
Something going wrong
Huh?
in the screen. Something
Huh?
going wrong in the screen. The screen letters are
Uh,
inverted.
the scheme got inverted. No? Now, now I
Oh,
think
no, not okay.
okay.
It remains same.
Wait. Actually, I made my PC laptop as a tab, and that makes this thing. Wait a minute. This is okay. This is okay. This thing was. This just a slide. I can write. Okay. So, with two level of system, the superposition of state is given as a1 t 1 e by e1 plus a2 2 e. Now, unperturbed condition, this value will give you this. But if we introduce some perturbation, then your total Hamiltonian will be a 0. This is time dependent perturbation. Now, now if we measure this value and do some calculation, then we will get the coefficient of A1 is nothing but E. Now this thing is known as coupled differential equation. So coefficient of state 1 is depend on coefficient of the state 2 and vice versa. So if, as we say, the coefficient square of coefficient is denote the probability. Therefore, the probability of psi one state, sorry, for state one is dependent on state two in time dependent perturbation linear. Now, this is a coupled differential equation. So, what which that means the the coefficient of A is comprised of coefficient is dependent on coefficient of two. Sorry, A1 is dependent on coefficient of A2. Now, if we need to get rid of this thing, then we need to make it a it will think just look at the equation first. This this part, this E2 E1 is H mu 1. Okay, so A2 dot you can write as now this thing is Hermitian. As this thing is Hermitian, then we can write now if you look at this equation, then A1 and A2, these two coefficients are out of phase. That means if A1 goes like this, then A2 will go like this. Both are out of phase. Okay. Now to get rid of the coupled differential equation, you can write A1t, let's say A2t I h dot T I omega 2 1 T 1 H T. Now, if we take this value as H capital E, okay, so we can write it minus I V A2T E I omega 1 T, and A2 dot T is I V star A1 T E I plus I omega 1 T, and A2T as minus A1T IV with I omega 2 1T IV star E I omega 1T. Now, if you take the double derivative of A 1. Then their value will be IV a2 dot E I omega 2 1 t plus I square V omega 2 1 t it, it so written as and point is I V star A T. Now in for A1 equation, if you put a the value of A2 dot, similarly if you substituting A2 dot, now this is the expression. Therefore, this is the way to solve this little bit longer and time taking derivation of coupled differential equation to do this equation which only depend on the one function, one coefficient. So first derivative is depend on the coefficient of other state, but second derivative, if you take the second derivative, then it will you can easily get measure the only dose coefficient of the dose that state to get the value. So this is some homework that is given in that module that I just want to discuss it in this forum. So this is the solution. With this, I think we are we now close this session. But in next session we will do uh, uh, we will have a discussion on the second assignment number 2. Beforehand, just I will say you just look at the question module, and so that we can discuss it the uh, next meeting. And the next this week 2 lecture is only based on the how it goes. Now in this case, the the derivation from just week 1 and first three lectures of the week 2 is only based on the two level of system. Now in this week 2 lecture we will find out the derivation is mainly focused on the multi level of calculation, which is more real, and which is more necessity to do for the scores. Okay, so with this I think we can stop it now. If you have any question, you can feel free to ask.
Sir, when will be our next class? Next Monday.
Next class will be next Monday 7 to 9. So my class will be on every week, Monday 7 to 9.
Okay, sir. Last week, two classes had coincide in the same time.
Yeah, yeah. So another course by Sevi, she will take on tomorrow. Okay.
Okay, okay.
So with this, if you have any question, you can ask, or we can call it a day.
No, sir. Thank you.
Thank you.